Okay, so first I'd like to thank organizer for arranging this wonderful event and giving me the opportunity to talk here. So today I will talk about this pre-thermalization in a randomly kicked system, many body systems. Okay, so this work is done with my collaborators, the Aditya Kandu. He is a postdoc in Luxembourg University, and Tanayana from BITS Hyderabad. And the calculation are mostly in this paper done by Aditya. And we have submitted this in PRB, and we have received the referee report, and those are mostly positive. Okay, so this is my brief outline of my talk. So I will, for the motivation, I will start from the periodically driven system, and then we'll see that what a prethermalization we can see in the periodically driven system, and what is the fate of this prethermalization when you have this randomness in the drive. Okay, and finally I will conclude. So, like if you have a many body system, which is a generic system, that is interacting systems. Now, if you give a external periodic drive in the system, that means you are constantly putting energy in the system. So, in that case, what happens? The system eventually go to the infinite temperature state. So, the energy is constantly growing. Okay, so then now we know that this periodically driven in the system that can give us many exotic phases that does not have the static analog. But what happened when this is the heating, then these phases are washed out. Okay, so then the question is this: how to like minimize this heating? This is the question. And here one thing is that if you drive with high frequency, that what happens? The system cannot synchronize with the drive, and then you will get a long time, which is sometimes exponentially long. And when the system does not absorb energy from the drive, and you can measure things there. And because it is exponentially long, so it is meaningful. Okay. So now the natural question is that what happens if we break the time translational symmetry in the system? Okay. So then whether this phase exists or not. Okay. So then here this quantum many body systems people have studied for the systems which have the finite bandwidth, this type of systems, and it has seen that there is a slow relaxation for the these quasi-periodic drives. Okay, so then what about the classical systems and purely random drives when we are giving the drives which are random? So here is the work, similar work, but they considered more structured drive. And here we consider like random drives, and also our approach is also different than them. Okay, so model here we consider a like this is the schematic diagram of how the driving is done. Okay, so this is the you can say space, that is the position of the rotors, and this is the time. So we have like there are some and this is the like map of the systems. Okay, so here this L, this is the, let's say this is angular momentum of the system, and theta is the like angular position. Okay, so when you have a kick, then you have this term is there, and when there is a missing kick, so then this angular momentum does not change. So you have, and this is the free evolution. So this is the like free evolution followed by the either kick or not kick. So if you consider the Hamiltonian for the system, so this is this is the Hamiltonian, where the first is the kinetic energy and the second is the interaction energy between the rotors. So this is a rotor. You can think of this as a like a ring, and there are many particles which are moving, and there is a external like pulse you are giving to the system as a kick. Okay, and then kappa is the kick strength. So now if this delta, if is t minus some n tau, so then this is the periodic drive. So what happens? We here consider that there are some missing kicks. Okay, so there is, it is not the periodic. So there are some missing kicks, and the missing kicks are we are considering with a distribution. This is called waiting time distribution, where waiting time is defined as tau w is equal to L tau. Okay, so here L is a positive random integer. Okay, so okay, so now before going to this random case, we consider the like theoretically derived case, that is the Floquet case. So where this tau w, that is the waiting time, is always tau. So in that case, what we get, that if we just calculate the kinetic energy, average kinetic energy of the system, so we can see that there is a long plateau, and then finally it goes to the diffusive regime. Okay, so the energy source diffusion. And then we can see that depending on the k, so k is the only unitless parameter of the system, that is the kappa and tau. Depending on that, you have this, what is the length of this, that is lifetime of the pre-thermal state. So this we are calling pre-thermal because it eventually go to the like infinite temperature state, but before that it thermalizes. And then the lifetime of the pre-thermal state can be found as e to the power 1 by k. Where k is the kappa tau. So if k is small, then you will have then you will have a long time. Okay. So then here we consider this like random drive, and then waiting, we consider this waiting time distribution. So like these are the, let's say the our kicks which we are going with the n. Okay, n is the number of events. So we have sometimes there is a kick and sometimes there is a missing kicks. And then if you consider the time between two consecutive kicks, so that is our waiting time. And this if it follows this type of distribution. And then if we the distribution, if we plot, it will look like this one. And then for this case, if you calculate the kinetic energy as a function of time, so here also we considered for different gamma here and different k. So we can see there is also region, but it is not like the previous case. So when the energy is not growing much, and then finally it is go to the like it grows. And then if we just scale the x-axis with this k square s, where s is actually called surprisal. So it is nothing but the like entropy that is introduced in the system due to the randomness in the drive. So it is defined in that way. So one can calculate also the surprisal for this case. And then if we just rescale the x-axis, so you can just collapse these curves. So in that case, this diffusion constant of the systems, you can this is proportional to this s gamma k square. So what happens if we have the like periodic drive, then it is only k square. So now it is normalized with this s. So this is the surprisal. And similarly, we get this T star is 1 by s gamma k to the power a, where a is between 1.9 to 2 within the error. So this is the T star. Previously it was the exponential long. It was now it is the algebraic one. Okay, so and also then we consider this binomial kick sequence also, where the p is the probability of occurrence of a kick, and 1 minus p is the probability of not a kick, of a missing kick. And then we do the similar things, and here also we find that T star is proportional to this one. Okay. And then here we consider more structured drive. So this is like two-Morse drive. So in that case, there is this waiting time is not in finite, that there is a cutoff. So this is only tau, 2 tau, and 3 tau. So in that case, we getting this T star, which is exponentially long, e to the power 1 by c by k. Okay, so but previously for the purely random case, it is 1 by k. So here we just giving some conjecture here with this like phase space, defining the phase space entropy, considering that P gamma T, this is the phase space distribution with two consecutive kicks. And then if we just relate the Fisher information, which is nothing but the expectation of this quantity, and there is a relation, that is the time Fisher information uncertainty relation. If we just consider this two case, and then we can write this one, and then finally this delta ST, that is the phase space entropy. We are calling this is the proportional to the S, that is the surprisal due to the random drive. So we can consider that because this entropy is additive in nature. And from there we have this relation, and then we see that previously in the periodic case that the dynamics driven by this k parameter, which is modified in that way. Okay, so that we can see in the pre-thermal lifetime for the random case. Okay, so this is the our conclusion that for the random drive case, we say the algebraic suppression of heating, and then and if you had the structured drive, that is we consider exponentially long time for the pre-thermal lifetime, and then we give some conjecture from phase space entropy and Fisher information. Okay, thank you for your attention.
Any questions?
So the average energy of the pre-thermal saturation value that can be tuned in the model?
That depend on the K, that is the strength of the drive. Okay, that it can change.
So can you explain why the pre-thermalization time goes as exponential of 1 by k?
Okay, so that one can do with that using the resonance condition and that some Gibbs ensemble. So if we, because there is pre-thermal state, we can define a generalized Gibbs ensemble there. Okay, and then if we we consider that initially the system is not absorbing energy, and then when there is a resonance condition, so that it means that difference between the angular momentum of two consecutive rotors is proportional to this n omega. That omega is the frequency of the drive. So then the system starts absorbing energy. If you consider these two things, then one can show that it is going there.
Okay, thank you.
I think I have a related question. So in the standard case, the thermalization happens because the modes are coupled in a chaotic system. So you inject energy goes into all the modes. In the case where there is some kind of randomness, why is this prevented?
So here, because as I told that in the periodically different cases, so also this happens for the resonance conditions. Okay, so some resonance happens. So here, when you have the random type, so then more resonance channels are opened. Okay, so and then it like happens more early than the previous one. So sorry again. No, resonance here it is like this angular momentum. So this is the rotor system. So there is a difference between the two angular momentum, two consecutive rotors with the frequency of the drive. Okay, so that is the natural frequency of the system and with the drive of the frequency of the drive.
Sorry, I thought, so you have this algebraic behavior for random drives, right?
Sorry, algebraic behavior for random drives.
And then for quasi-periodic, you have
quasi-periodic still it is exponential.
So is this like a very generic statement that for any model, if I quasi-periodically drive it, it will stay longer in pre-thermal state?
It is like mostly it is seen, but I don't know it will be more general or not, but it has been seen that this quasi-periodic, this exponential thing is there, right? So in this the paper we consider, they also seen the exponential thing. So also their drive protocol is different. My drive protocol on this is like two modes, but they consider differently. Okay. It is still there.
Okay.
Okay, so let's thank our speaker.